Hey everybody, wanted to provide an update on the home power monitoring project. Again, this is just a project that I'm working on in my spare time. I'm not in any sort of rush to get it done, but I wanted to document all the things I'm going through and share it with you. For those that missed the last video, I'm working on monitoring the power usage in my house by attaching a sensor around the main lines that come into my breaker box, which is actually just on the other side of this wall here. Using a sensor like this, you just open it up, put it around your mains, close it, and then you'll get a voltage out on this end that is proportional to the amount of current that's coming through the sensor. And this is very common. There's lots of products that can do this for you. They're very expensive, and so with an electrical engineering degree, I figured this is something that I might be able to accomplish myself. And so I have no idea if it'll work in the end, but I'm trying. And so the latest update is, as part of this, I need to build a precision rectifying circuit. And because the signal that comes off of this is extremely small and dirty, and so we need to clean it up, filter it, and amplify it and rectify it, because it's an AC signal and we need to turn it into sort of more of a DC signal so that we can read it with something like a particle photon or an Arduino or something like that. It doesn't matter what the platform is once we have a nice clean signal to read. And so in order to do that, I needed to purchase some op amps. So I did, and the first problem I ran into was I ordered the wrong package type. So when you order parts like this from DigiKey and Mauser, places like that, a lot of times the same part will come in various packages, meaning you can get what's called a DIP package for a part like this, which stands for dual inline package. I guess the P is redundant. Anyway, it's got the nice legs on it so you can stick it in a breadboard. And then there's the SOIC package, which is more of a surface mount. The legs come out and then they go like this, which is good for setting it on a printed circuit board for surface mount soldering and things like that. That's the package that I ordered because I wasn't paying attention. And so I got those parts in. I didn't want to wait. So I ended up hand soldering wires onto it so I could connect it to a breadboard, which was one of the hardest soldering jobs I've ever had to do. Believe it or not, I've done some pretty tight surface mount soldering, but this one was just a bear to solder. So I got that all in. Since I had to do that, I felt like I should probably test that I haven't burnt any of the op amps out, because I was holding the soldering iron on some of those pins for a long time. And so I did. I created just a very simple sawtooth signal with a particle photon. Actually, I found a library to do it because I don't have a function generator. Did that, did a simple op-amp circuit that just doubles the amplification of the input signal, and had this beautiful input-output signal on my oscilloscope on both of the op-amps on the chip that I soldered, and so everything worked out really nice. The op-amp was working, so I was ready to start building the precision rectifying circuit. And I just found CR Magnetics. It's the one I showed in the last video. Has this handy-dandy schematic that you can build to amplify a current transformer signal, just like the one that we have. So I started to build this on the breadboard, and man, I got mixed up. I got all mixed up. It's been a while since I've done some of this stuff with op amps, since college, in fact. And so where I ultimately ended up is I fried the op amp that I spent probably an hour soldering to get back together. And so that I ruined that, and so I have more and I could solder more. I ordered 5 of them and I only burnt out the one, but each part has 4 op amps. Anyway, I have 4 more that I could use, but I didn't want to do that soldering again, so I went back to DigiKey. I ordered the correct package because, again, I'm not in a hurry to do this, and I just figured I'll just wait a couple days and pay the few bucks to get more parts. So those are on the way so that I can get back to the drawing board on creating the precision rectifier circuit. But also, I realized, if I'm going to build this in stages, because there's different stages to this circuit, I need to be able to see that the signal that's coming off of this is doing what I expect it to do, rather than just build this whole thing up and then magically hope I get a clean signal on the other end. And so if you remember from before, I think I mentioned the signal, if you just plug it into the oscilloscope, it doesn't show anything, it's just noise. But I was able to turn the knobs and push the buttons on the scope to such a degree that I was able to find the signal. And so I just want to show, I'm going to flip to that video here where I show you how I found the actual signal coming off of the current transformer. Before I start building precision circuitry to amplify and clean up the signal that I'm getting from the current sensor, I wanted to at least find some semblance of a signal coming off of the current transformer to know that that the stages of this amplifier that I'm going to build are actually doing what I expect and working, so that I can debug any issues with that. And so this is what my scope looks like when I turn it on. This is a Rigol DS1054Z, and I've got two probes plugged into it. The yellow one here is connected to the output of the current transformer that you can't see off screen here. It looks like that. And the other one's just floating. I was using it to test the operational amplifier to make sure everything was working as expected there. And so the scope tries to be helpful and says, hey, you have two probes connected, and here are the two signals, and it separates them on the screen for you like this. And the blue one, like I said, is disconnected. The yellow one, or this yellow trace up here, is what's connected to my current transformer. And so to clean things up, I'm going to turn off channel 2 here, which leaves me with this. The scope offsets it, so what I can do is I can just pull that back down to a 0 offset. There's probably a quicker way to do this than to drag it like this. Again, I used to be pretty good with an oscilloscope back in college, but that's been a lot of years, and so now I just kind of push buttons to figure things out. So anyway, so now it's centered around there. That's what the light turned on. I'm going to go ahead and turn it off. And you don't really see much of a difference. It looks about exactly the same. Turn it back on. You know, that thing might get a little higher, I don't know, but it's not giving me the nice AC sine wave that I'm expecting from the transformer. And again, with this specific transformer, it's 330 millivolt total output swing when you have 200 amps going through it. This photography light I have here is 1 amp, almost on the nose. And so at 1 amp, I'm only looking at a couple of millivolts of a signal that are buried in this line right here that I can't really see. It's not this, because you can see 200 millivolts per stage, and so if we go up, that's like at 200 millivolts. So that's some sort of noise that we're seeing there. And so as it turns out, there's a simple way through just messing around with the scope to find the signal that's buried in there, and it's really just a matter of scale. And so right now, I don't know how well you can see it, I am sampling at let's say that's 1.0 gigasamples per second. And so if I just lower that and don't sample it as often, I'm going the wrong way, like that, just keep going, you'll start to see almost like it's the wave, it's like waving, and you can't see it super well because it's low. So what if we just turn this up and change the scale this way? So we're changing the scale both horizontally and vertically here. And then now if we do that, we have some thing that looks like a signal a little bit there. So I'm going to turn the light off. You'll see that it goes away. Turn it back on. And now you can see buried in all of this noise and all this sort of dark yellow is the signal, and this light yellow is just a lot of the noise that we're getting on the line. Again, these leads are pretty long, so they can pick up all sorts of noise like an antenna in the air. And so, but there's our signal. And then we can do one better here. If we go to the acquire menu, and I've got this mode set to normal. If I change it to average, it's going to get rid of a lot of that peak noise. So I'm going to do that. And now you'll see I have kind of this dirty sine wave, but that's what the light turned on. Let me turn it off. You'll see that goes just about to a flat line there. Turn it back on, and now I've got my signal. So here, buried beneath all that noise, is the signal I was looking for. And again, I'm at 10 millivolt steps here. So each square of this grid is 10 millivolts. And I'm not sure how well you can see that on the video, but that means this first line above 0 is 10 millivolts. This is way down below that. So right about where I expect it. My VP to peak is listed. It's bouncing all around, but somewhere around 4 or 5 millivolts. And then when I turn it off, it goes down to about 2 millivolts. So I have some sort of offset that the oscilloscope is picking up there around 2 millivolts, but when I turn it on, 1 amp comes through the sensor, I see about that 1 to 2 millivolt jump that I'm expecting. And so here we have a signal that we can work with. We can pump this into our precision amplifier circuit that we're going to build and start to see, you know, is it rectifying it? Is it offset at the right voltage? Everything I want to make sure before I plug this into something like a particle photon or an ESP32 board, I want to make sure that the signal is doing what I expect so I don't fry any of my boards or anything like that. And so this is really great. I found the signal buried underneath there, and now we have something to work with and go forward. Okay, so as you can see, we have the signal, it's there and I can see it. So now as I build the precision rectifier circuit, I'll be able to see that the signal is indeed doing what I want and I expect, so that we can measure it with a maker platform. And so that's where we're at. I'm waiting on parts. I've also started playing around with Circuit Lab to be able to simulate, because after I burnt it out, I obviously connected some things wrong, so I figured I should actually probably build this out in a program and simulate it to make sure that the part choices and things I'm doing work. And Circuit Lab, maybe I'll do another video on that to help me design the amplification and rectification circuit. And so that's where we're at, and I will keep you posted as we hopefully make progress on this. When I get the parts in, hopefully I'll be able to get something together that does what we need to the signal. So that's going to do it for today's episode. Any thoughts or comments, please stick them down below the video here. And as always, I appreciate you watching and hope you have an amazing day.